Good morning again and welcome to the Innovation Exchange and today's webinar. The value of air leakage testing in large commercial buildings is the title of today's webinar, and it'll be an overview of study findings. If you're having any challenges today, or if you can see the screen but you're having sound challenges, don't be afraid to contact Anna Jursic. Her email is on your screen right now, or you can also find her email on our Faces of CEE staff page on our website. I am Megan Hoy, the Engagement Coordinator for the Innovation Exchange and your host for this morning. If you have any other questions about engaging with CEE and the Innovation Exchange, which I will touch on at the end also, feel free to contact me at any time. At the end of this webinar, we'll have at least 5 to 10 minutes to review questions and answers from today's content. We encourage you to enter any questions you might have in the Q&A dialog box on your screen, or if it's not on your screen, you can hover over the desktop menu bar at the top, and hopefully the Q&A box will pop up there and you can open it from there. I'll be kind of looking over questions throughout, so again, feel free to enter them at any time. If we don't have time to get through all questions today, we will post all questions that are asked along with answers on our webinar archive page, along with the slides that Dave will be presenting and a recorded webinar. The Innovation Exchange puts out a number of webinars each year. Our next one is going to be held on Thursday, December 12th, and if you can join us at this same time, 11 a.m., and it's going to be titled Counting the Capacity That Didn't Hatch, the Rate Mitigation Effect of Demand-Side Management Programs. Our program manager, Jenny Edwards, will present an analysis comparing the cost of DSM programs to the cost of developing new central generation resources that would have been built had demand not been reduced. And just one quick housekeeping bit, just a reminder to everyone to make sure you're muted on your end so that we don't have any unwanted noise in the background throughout the webinar. Today I'm happy to introduce our presenter and primary investigator on this project, Dave Bohac, the Director of Research here at Center for Energy and Environment in the Innovation Exchange. Dave has had more than 30 years of experience in energy efficiency and indoor air quality research, with an emphasis on creating and analyzing advanced diagnostics and monitoring methods. He has directed a variety of applied research and program development projects, working on issues from duct leakage and ventilation system improvements to hot water and space heating combination systems, performance, and diagnostic protocols for weatherization. Not only has he collaborated on research with the state of Minnesota, but also with ASHRAE and with the Department of Energy's Building America initiative. He also serves as the technical advisor for the Center for Energy and Environment's Community Energy Services, or CES, program that provides home energy visits in many communities across Minnesota. Dave holds an MSc from Princeton University and a BS in Mechanical Engineering from the University of California, Davis. He previously worked as a research assistant at the Center for Energy and Environmental Studies at Princeton University, but I am pleased to report that he has been working with CEE since 1988. Before I pass it off to Dave, I just wanted to acknowledge the Minnesota Department of Commerce and the Division of Energy Resources for their support through our Conservation Applied Research and Development Program in the state of Minnesota, and the funding that helped make this research possible. So with no further ado, I will hand it over to Dave, and we will we'll get started.
Okay, thanks, Megan. I think before we get into the content, I thought I would go through just a brief explanation of what we use for a building tightness specification for larger buildings. So if you're used to doing testing on residential buildings, you've probably been using CFM50, or the amount of air that it takes to pressurize or depressurize a house to 50 pascals, and then sometimes that's normalized by building volume to get ACH 50, or it's normalized by floor area. So things are a little bit different for larger buildings. One, we use 75 pascals as a reference pressure, and so when we test, we want to be measuring the airflow to pressurize or depressurize to 75 pascals or 0.3 inches of water. And then for normalization in the United States, what we use is the building envelope area that includes all 6 sides of the building. So that's going to be your exterior walls, roof, and floor. And just to maybe get you started on what some reasonable numbers might be for this specification, NIST has been putting together this database of test results from U.S. buildings, and right now their average is 0.72 CFM at 75 pascals per square foot, and that range is quite wide. It goes all the way down to a low 0.03 and up to 4.3. As far as what some of the code requirements are out there now, the U.S. Army Corps of Engineers has really been leading this effort the last 5 years or so, and they have a standard right now of 0.25 CFM per square foot, and they've tested over 300 buildings to meet that standard, and right now they're averaging about 0.16 CFM per square foot. The new version, or the IEC version 2012, does have a compliance path for whole building air leakage, and the standard for that is 0.4 CFM per square foot, and that's been adopted by 7 states. And in the state of Washington, they now require that buildings over 5 stories must do a whole building test, but they don't have a standard that the buildings have to meet. And then also with the City of Seattle, that all buildings have to perform the test, but again, they don't need to meet a specified value. So, question is why do we care about building air leakage? And I'd say 20, 30 years ago, the common theory was that we weren't so concerned about large building air leakage. One of the reasons why is that mechanical engineers tried to design the heating and cooling equipment so that the buildings were pressurized. And so it was thought that when a building was pressurized, there wouldn't be much infiltration air, and you really didn't need to worry about the envelope leakage that much. But of course, in a lot of our buildings, they're only occupied half the time, and the HVAC system's only running half the time. So you've got maybe half the time when the system's not running, and for that whole time, you will have infiltration since we won't have any pressurization from the HVAC system. And we also know from experience that many times the HVAC systems just aren't set up quite right and don't achieve the type of pressurization or level of pressurization that the mechanical designers desire. And in fact, 20, 30 years ago, Andy Pursley at NIST conducted some tracer gas tests on large buildings and was finding that the kind of the combination of the outside air ventilation rate and the infiltration rate was considerably greater than the minimum ventilation rate that was required for the building. So it became apparent that we did need to worry about envelope leakage. So here's, we'll start out with a simple diagram. Here's a 4-story building, 60,000 square feet office building, leakage 27,000 CFM at 75, or normalized at about 0.5, so a little bit tighter than the national average. We're starting out here, the diagram on the left, inside temperature is the same as the outside temperature. The HVAC system is off, no infiltration, no exfiltration. But we want to anticipate that we are going to have some wind under those conditions. We'd like to pressurize the building. So in this case, we have a rooftop unit that's running, and it's bringing in a little bit over 10,000 CFM of outside air for ventilation. And we're exhausting about 2,000 CFM either through the exhaust fans in the building or some kind of active control to open up relief dampers to relieve some of that air out of the building. So consequently, we're pressurizing the building by about 12.5 pascals or 0.05 inches of water, which is a fairly typical design target for HVAC systems. And so the difference between the outside air coming into the rooftop unit and the exhaust air is about 8,400 CFM, and that's all going to be exfiltration out of the building envelope. So just to give you an idea of what this rooftop system looks like, we've got outside air coming in from the right, mixing with the return air coming from the space, going through a heating coil and a cooling coil, and then it's supplied to the space. So in that system, there is no relief air or exhaust air, and we've got the 2,000 CFM either going out through exhaust fans, say a toilet exhaust, or again, some kind of pressure relief. A lot of buildings, instead of a simple rooftop unit like that, will have a air handling system. And in this case, we have a supply fan and a return fan. And then we have a series of dampers that control the mixing between outside air and return air. So in this case, it's a relatively simple system. It's a constant volume. And the supply and return fans just turn on or off depending on the building operation. So they'll turn off when it's occupied, or I mean they'll turn on when it's occupied. And then the dampers are set to control the amount of outside air and the relief air. So in this case, we have the dampers open about 25% to their minimum position to bring in that 10,500 CFM of outside air. The mixed air dampers are at 75%. And then the relief air dampers are set so that hopefully you get the amount of relief air that gives us the proper balance between outside air and relief air. And that's going to be, in this case, the 2,075 minus what's going out the exhaust fans. So we're back to the same diagrams on our building, but now we're looking at outside temperature of 20 degrees. And on the left, the HVAC system is off, so we have the stack effect working on the building. And you can see, you know, the pressure profile here on the buildings. The blue arrows show that we have infiltration at the bottom, or negative pressures at the bottom of the building, positive pressures at the top of the building where air is going out of the building. And in this case, the neutral level isn't quite at the middle of the building. We have more leakage at the top and then at the bottom, which is why the neutral level is closer to the top than bottom. Now in the diagram on the right, we're turning on that HVAC system. And so now we're pressurizing, or we're bringing more air into the building than we're exhausting out of that exhaust fan. And then you can see the pressure profile on the right. So previously, we had 12.5 pascals across the entire building shell, but now with the stack effect, we've got more than that at the top, but now we're down to just 1 pascal at the bottom. So we've lost almost all ability to control infiltration if you have any kind of wind at all. And in fact, now we've got 0-degree weather conditions on the right, and you can see as we get down to 0 degrees, we're actually going to have some infiltration at the bottom of the building, even though we have this system that's supposed to be pressurizing the building. And we've got about 290, 300 CFM of infiltration in those conditions. So, and that's not giving us any protection of wind at all. So in this case, now we have that same conditions, 20 degrees outside. We've got the rooftop unit trying to pressurize the building, but now we have a wind that's moving left to right in the building. And you can see on the windward side of the building, these arrows actually should be going in the opposite direction, but we do have some significant infiltration at the bottom, exfiltration at the top, and then exfiltration down on the leeward side. And in this case, we get a little bit over 400 CFM of infiltration into the building. So you can see what started out to be a good pressure control strategy in mild weather really starts falling apart as it gets colder and windier. And what I've shown here is just two relatively simple systems, a rooftop unit and a constant volume single zone system. Things get more complicated from there. Many of the air handler systems are set up to economize, which means as the air temperature outside drops below the inside temperature and we still need cooling in buildings, we start bringing in more outside air than we need for ventilation to help with cooling the building. So in that case, we'd be opening up the dampers. In this case, we went from 25% to 60%. Now we're bringing in about 24,000 CFM. And these dampers on the relief side need to be adjusted so that we still have about our 8,000 CFM differential between outside air and relief air. And typically what will happen is relief dampers will follow exactly with the outside air, or they'll lag by, say, 5–10%. In some cases, there might be an active control where the building pressure would be used to control either the relief air dampers or possibly if you put a variable drive on the return fan, it could be used to control the return fan speed. And things get even more complicated and potentially messier when you put VFDs on both of the fans. So I'm not going to go into that right now, but I'll just say that as you get into more complex systems, the likelihood of being able to have your pressure control work properly kind of goes down accordingly. So here we have a graph that shows the effect of varying amounts of pressurization air that's being brought into the building. So this is about a 60,000 square foot elementary school, single story. The leakage in this case is about 0.75 CFM at 75 per square foot, or 44,000 CFM 75. We're using a CONTAM, which is a multi-zone airflow modeling tool to get these results, and we're inputting the kind of typical meteorological year data and outside temperature and wind speed for Minneapolis. So along the x-axis, we have different outside temperature bends. So we're going from -20 all the way up to 90 or summer conditions, and our different lines are showing different amounts of pressurization airflow. So in the case of the blue line, the amount of air that we're bringing in is exactly matching the amount of air that's going out, and so we're not pressurizing the building at all. And then in the top line, we actually have more air that we're exhausting than we're bringing in of outside air. And the violet line, or the fuchsia line, is a differential of about 3450. And then the orange line is twice that, about 6900, which would produce typically a 4 Pascal pressure difference. And then the green line is the most amount of pressurization air, that's 17,250 CFM. And that would typically pressurize the building to 17 pascals. So 17 pascals gives us a pressure that's above what people would normally design for. And you can see that, especially in the colder weather, we do have significant amounts of infiltration in the building. So even though we have more outside air and more pressurization air than we're designing for, there's still a significant amount of infiltration. And if you don't achieve that amount, say for the green, and have less than that, then the amount of infiltration that you'll be getting in the building will just go up accordingly. So this is the same information now, but just with a tighter building. It's now at 0.25. So in this case, you can see the building got tight enough that the amount of flow imbalance that we had is controlling infiltration quite well. And in this case, the building's occupied about half the time, so when we're at the 17,000 or the 6,900 CFM, in those cases, we pretty much have eliminated the amount of infiltration during the occupied period. What remains here is the amount of infiltration during the unoccupied period. So just to give you an idea of what that impact is, the top row here is the average infiltration over the course of the year in CFM. And then the second line down is that converted over to air changes per hour. And the next row down is the load that's placed on the building from that infiltration in therms per year. And then the percentage is the percentage of that load as the amount of total space heating load on the building. So you can see in a leakier building at 0.75, when we're exhausting more air than we're bringing in, that in that case our infiltration load is actually 19% of the total space heating load in the building, and we're going to be paying another $4,200 to pay for that infiltration. As you ramp up the amount of pressurization flow in the building, then that is going down accordingly. And then when we take a look at the tighter building, things start looking even better. So if we get to about 3450 of flow imbalance, now our infiltration loads are down to 5%, and the amount of cost for that is about $1,000. So we're going to transition into some information about from air leakage testing, and before we do that, I just wanted to show you this video that shows kind of setup and a test and process.
Uncertainty in future energy prices and environmental implications are prompting building owners to use energy resources more efficiently. The National Institute of Standards and Technology estimates that air infiltration through leaky envelopes is responsible for 33% of heating energy use in U.S. office buildings. U.S. Army Corps, other federal government entities, and even the state of Washington have established requirements for whole building air leakage testing. As a result, there's been a dramatic increase in the demand for large building lower door air leakage testing. Until recently, lower door testing was mainly performed on small residential and non-residential structures. Advances in equipment and software have made it much easier to conduct multiple fan lower door tests on large buildings. Check out this walkthrough. The number of fans needed for an air barrier performance test is determined by the reference air tightness specification or standard. Identifying fan locations that will provide effective pressure distribution is a necessary part of the setup. There are many details and logistics to consider. Proper preparation is crucial. It is efficient to pack everything needed for a 3-fan system in one duffel bag, something about the size of a black duck blaster bag. This method saves time at the setup and teardown stages. It is helpful to have access to carts to move equipment from the staging area to the setup area. Lower door frames need to be installed securely. Equipment popping out of place during a test can extend the time required to test and possibly damage fans. Fans, speed controllers, gauges, tubing, and cables are installed next. When running extension cords, make sure each fan is on a separate circuit so that electric breakers are not accidentally tripped. The setup for a large building test is similar to those conducted in a house, just scaled up. Coordination with building management is key, as access to mechanical systems is necessary, and occupants can be affected when they are turned off. Bring a bag of wedges to prop open interior doors. Rooms along outside walls need to be left open so that all parts of the building are at the same pressure. 5 to 50% of building leakage can occur through intentional mechanical openings. Most test protocols require intentional openings within the test boundary to be sealed to a specified level. Sealing and unsealing these openings is one of the most labor-intensive and time-consuming parts of the test. Tarps, held in place by large hoods, and large garbage bags installed over rooftop ventilators that use 2-foot-wide carpet protector tape are some methods used to speed up the sealing process. It is good practice to measure air tightness with the building sealed and unsealed, marking the periods for both. The Energy Conservatory's new TechLog software allows you to control all of the fans from a central computer using one slide bar. Cat5 cable is used to connect EG700 pressure gauges to the computer. The software recognizes each gauge's serial number, allowing each pressure channel to be identified. A worksheet is used to gather information about the EG700 configurations, and that information is transferred to the software. While the software graphs the building pressures and the fan flows, periods of record are marked at predetermined building pressures. Typically, buildings are tested under both positive and negative pressures, so the test results page will show testing for both as well as the combined results. A report can be generated from these results. While the blower door test measures the building tightness, an air leakage investigation is necessary for determining where the air leakage is and how it can be sealed. Test findings also provide evidence for how air leakage can be reduced in new construction. Properly designed and tested tight buildings will be more comfortable, durable, and affordable to operate. This test was designed and implemented as a collaboration between the Center for Energy and Environment and the Energy Conservatory, and funded by the Minnesota Division of Energy Resources.
Okay, so I don't expect everyone to be a professional large building air leakage tester after that video, but hopefully that gives you a feel for what goes into one of the tests. And I would say it would typically classes to get people trained in for doing the test would be kind of a 2 to 4 day class just to get you started on that activity. So I mentioned before that NIST has been putting together this database of tests that have been done on large buildings. So Steve Emmerich and Andy Persley at NIST for the past 15 years have been compiling data from people. It's not a random set of data, but pretty much anyone who is doing the testing and would like to contribute to the database, they will gladly accept the information. And they're using it as a way to establish reasonable values for their air infiltration modeling work, and also to help the air leakage standards that are being considered across the country. So here's some of the results that they have most recently. They're up, as I said, up to about 387 buildings. Right now, their average is 0.72 CFM at 75 divided by the envelope area. And you can see that every group that's contributed has had a fairly wide range, you know, with mins being down at 0.11 or below, and then maximums being, you know, 0.64 all the way up to, you know, 1.75. So we're seeing a wide range of measurements. And as I indicated before, the Army Corps have been testing buildings. They're over 300, and they've been averaging 0.16 with a standard of 0.25. So quite a few of their buildings are well exceeding the standard tightness requirement. So you just see the distribution. It does have a fairly long tail to it. There are quite a few leaky buildings out there. And of the more recently of the buildings that have been entered into the database, about 20 to 25% of them are meeting the Army Corps standard. They've also been gathering information about you know, the type of building, the type of walls, year of construction, and so forth, and are looking for trends and information on building tightness. So they're finding that the offices, education buildings, public assembly, healthcare facilities tend to be a little bit tighter, and that the retail, restaurants, and industrial buildings are a little bit leakier. And as far as the wall assemblies, that the framed masonry, metal, and frame masonry are being tended to be a little bit leakier. It's interesting, maybe to be expected, that the larger buildings are tighter. In fact, when you get to buildings over 54,000 square feet, they tend to be twice as tight as the smaller one. I'm sure part of that is the level of detail that goes into some of the larger buildings, but I think that also has something to do with about the type of leakage, in that some of the largest leakage occurs at the roof wall interface, and if you have high-rise buildings, there's less of that perimeter per square foot than you would get on a single-story building. They're also seeing an effect with climate in that for the buildings that are in a cooling or heating-dominated climate, 3,600 degree days or greater, are tending to be about a third tighter than those in more mild climates. And one thing that's been interesting is that they're seeing very little correlation with year of construction. So these are buildings all the way from the 1950s to the current time, and if you kind of throw out the more recent buildings from the last 10 years that were all in a colder climate, really there's no correlation with year of construction and tightness for the last 40 or 50 years. Some of the buildings in the database are LEED certified, 23 of them, and those average at 0.29 CFM per square foot. So that is significantly tighter than the entire database, but they've been tracking buildings built with and without an air barrier, and if you compare those 23 LEED buildings to all the rest of the ones that have been designed with an air barrier, that the LEED buildings are pretty much fall right in line with that, or if anything, they're just slightly leakier than those other 56 buildings with an air barrier. Just to look at that point again, the blue bars are all the buildings without air barriers, and the yellow bars are the ones with. So you can see the significant impact that air barrier technology has had with getting tighter buildings. And so Steve Emmerich at NIST has been doing some modeling work to look at, what the energy savings implications are for building tighter buildings. So he's comparing buildings that are at on the leakier side at 1 CFM per square foot, and comparing that to tighter 0.1 CFM per square foot. And he's looked at buildings in 5 different climate zones and different building types, and he's using the CONTAM air infiltration modeling teamed up with an energy model to be able to calculate air infiltration rates and the impact on energy use on the buildings. So just to give you a little bit idea of what he's coming up with, for the Minneapolis area, a 2-story office building, he was finding out that the baseline, which again is the 1 CFM per square foot, the added infiltration comes out to be about 0.23 air changes an hour, and that drops down to an infiltration rate of 0.05 when you get to a tighter structure. And for that situation, the gas savings is about $1,800 or about 43% off the space heating use. For the retail building, similar kind of results, 0.22 air changes per hour from uncontrolled infiltration in the leakier building, and that drops down to 0.02 air changes an hour when you tighten up the envelope to 0.1 CFM per square foot. So we've done some similar type of modeling. This is back to that 60,000 square foot elementary school building again. In this case, we have a flow imbalance of about 3450, and we looked at different tightness levels on the envelope. At the very top, we have 2 CFM per square foot down to 1.25, and then the brown 0.75. And so you can see the large impact that you have when you get to a tighter shell. Very significant impacts as you go down to 0.4 and even down to 0.25. And after that, it appears that there's kind of diminishing return on getting buildings tighter. That the green is at 0.15 and the blue at the bottom is at 0.05. And for many of the outdoor temperatures, there's very little difference in uncontrolled infiltration between those two levels of tightness. So just to kind of reiterate that point, the top line again is uncontrolled infiltration in CFM, how that relates as far as air changes per hour in the building, and then the heating load and the percent of infiltration load on the total space heating load. So very leaky building up at 1.25, your infiltration would be 23% of your total space heating load. If you get down to a nice tight building, 0.1 CFM per square foot, you've almost eliminated that. And you can see by the dollar amounts that there certainly are diminishing returns as soon as you get to about that 0.25 down to 0.15 and below 0.15, that there's more limited savings to be achieved. So have a little bit of time to talk about the study that we've been conducting this last 3 years. We conducted air leakage investigations on 25 buildings. We did air sealing and pre-post air leakage tests on 7 of those buildings. 1 is just recently completed. We also did continuous building pressure monitoring and compiled HVAC operation data for 50 to 200 days. We're at about 15 of those buildings. And then we used CONTAM, a multi-zone airflow modeling tool, to be able to estimate the pre and post air infiltration and what the savings would be from tightening up those 7 buildings. So we're using that to compute the infiltration savings and then the energy savings reductions. So just briefly, here's pictures. We have 3 elementary and middle school buildings, a small office building about 27,000 square feet, a university library, which is one of the largest buildings that we've tested, almost 250,000 square feet, and then a newer building, about 55,000 library office building that was built in 2007. So we have buildings going all the way back to 1970 or 1936 was the original construction year. But of course, with the schools, most of those have had additions, so they've had anywhere from 2 to 5 additions along the way, so there are newer portions of the structure. So here's some of the results that we've obtained, and what's been nice to see is that they're very tight. So this column here under air leakage at 75 pascals divided by the 6 sides, we have a high of 0.19 CFM per square feet, and the tightest is actually below 0.1. And again, now the Army Corps standard is at 0.25, so in all of the buildings that we've tested, they've been 25% tighter or more tighter than the Army Corps standard. So maybe if we were rational people, we just would have given up at that point and said, these buildings are tight enough, they probably don't need to be any tighter. But we went ahead and did air sealing work on these buildings. So here's the distribution of the Army Corps buildings, and you can see that red dashed line, that's where all of ours would end up. So we'd pretty much be in the 85th percentile or better, and our 7 buildings are, the average on those is 85% less than the U.S. average. So we have very tight buildings here that we tested. Again, we're kind of wondering if maybe this has something to do with the cold climate, that just the buildings overall in Minnesota are tighter, or whether we just picked 7 or 8 buildings that happen to be very tight in Minnesota. So as far as the air leakage investigations, most of the buildings we had infrared exterior scans, followed up by visual investigations using smoke puffers to identify leaks. A lot of that focused on the roof wall joints. In this case, you can see in the infrared that we have a canopy coming into an exterior wall, and we have leaks where that canopy is coming into the exterior wall. You can see the fluted roof deck, and you can see light shining in from the outside into the interior space, and that was treated with a foam product in order to seal in this building. So we don't have enough time to really go through all the work. I just want to be able to summarize here the effect that we've had with the air sealing work. So this table shows in the pre, it's our CFM of leakage at 75. So here's the pre and the post, and then the reduction. So we're getting reductions anywhere from 3 up to 17%. And these buildings are ordered with the leakiest being on top and the tighter ones being further below. In general, until we hit our community college building, we were seeing greater reductions in general for the leakier buildings. The community college building didn't quite follow that trend. So one thing I should say is that in all these cases, we followed up the air sealing work with visual inspections, with smoke buffers to see if the leakage has been removed. We've had infrared inspections, and across the board, the stuff that we were seeing with our infrared before the air sealing work has pretty much gone away. So what we've identified has been sealed, and overall we're getting about a 9% reduction in air leakage on those buildings. This summarizes the amount that has been spent on the air sealing work. So that was kind of a minimum of $1,100 where we did very targeted work on the library and office building, up to $26,000 that was spent on the one of the elementary schools. So the other columns are actually the dollars spent in order to achieve a CFM 75 reduction, or the dollars spent that was used to achieve a reduction in the equivalent air leakage, or leakage area, I'm sorry. So in general, you can see that the amount spent was higher for the tighter buildings, $65,000 spent per square foot of EQLA reduction. The one outlier there was that library office where, again, we had a very targeted leak and did a targeted amount of air sealing there. We've been compiling the information and comparing it to what we originally obtained from the contractors and have been getting some interesting results. So here on the right side, we have the contractor estimates for 4 buildings of when they were going to be doing the air sealing work, the amount of area that was going to be sealed. So you can see that a lot of it in these cases was the roof wall joint. And then we compared that to the reduction that was actually achieved here in this row. And the column on the right is just the measured leakage reduction in EQLA over the contractor estimates. So this was fairly disappointing that overall we're seeing about 20% of the reduction from what the contractor actually estimated. And what's really concerning is that the elementary school here that we measured an EQLA of 9.6 square feet, and the contractor was estimating that they would be getting a reduction of 17 square feet with their air sealing work. So they thought they were going to be sealing more leakage than the building had in it to begin with. So some real concerns here about the ability to do accurate estimates of the amount of air sealing that can be achieved in these buildings. So I'm not sure if it's just because these are very tight buildings and they're used to running across leakier buildings. I'm certain that's part of it. So for all of these buildings, we're going to be running them through the CONTAM multi-zone airflow modeling tool. And we've got that information compiled now for 5 of the buildings. And so here on the left side is we've used the utility bills to determine their annual gas use for space heating is in that column. And then the next column that's marked infiltration is what comes out of the CONTAM model for the estimated infiltration load, space heating load. And then this column next is the percent of the infiltration of the total. So you can see that's varying between 9% and 35%, which is pretty much in line with NIST has been seeing in their modeling work. Again, this is just the leakage reduction is the leakage reduction in CFM 75. And then the savings is in therms per year. And then we applied the gas cost from about a year ago to come up with savings, annual savings. And then the next column over is the cost for doing the air sealing work. And then the final column is the payback in years. So you can see some fairly disappointing results there that at best in that library or office, we're getting about an 11-year payback on that air sealing work. And in some of the cases, we're getting paybacks over 100 years. So certainly in these group of very tight buildings, the air sealing was not very cost effective. We need to be wrapping up fairly soon. I will say that as part of this testing, as the video showed, we were sealing up the mechanical penetrations and dampers. At the end of those tests, we unsealed them to see what the change in the leakage would be. And I think in the recently completed ASHRAE research project, we're doing much of that same kind of measurement. And we're seeing that the leakage through the mechanical systems range anywhere or increase the building envelope leakage anywhere from 17 to over 100% in these buildings. So very significant leakage in the mechanical systems. And you've got to remember that when those mechanical systems are off, which in a lot of buildings is half the time, they become part of the envelope. So when they leak, it's just like you have a leakage in the envelope. So I think this is really something that needs to be focused on in the future. It was nice to see that buildings that were built more recently have had lower amounts of leakage, so the dampers in newer buildings tend to be tighter. I talked a little bit about the pressure measurements. Don't have a lot of time to go into that, what we have for results right now, but this shows you the binned information that we have. We've split it up into 5 different outside temperature bins, and then split those pressure measurements up into unoccupied and unoccupied periods for the different buildings. So one thing that is interesting to see is I'll pull out the information for the 20 to 45 degree outside temperature bin, and the filled in circles are for the occupied periods, and the open circles are for the unoccupied periods. So again, what a lot of mechanical designers would strive for would be about 12.5 pascals of positive pressure. So you can see that really in no case for these mild temperatures, relatively mild temperatures, are these buildings achieving that level of pressurization. It is good to see that pretty much across the board that the occupied times have a higher pressure than the unoccupied times. So the HVAC systems are tending to pressurize the buildings, but they're just not getting the amount of pressurization that one would desire, or what most mechanical engineers design for. And if you look at the rooftop measurements, we're going to see higher pressures up at the roof, and that does occur. And there is one interesting case here of this high-rise office that's over a 10-story building. You have significant depressurization at the bottom of the building and fairly significant pressurization at the top of the building. So just to summarize some of the key points for the buildings that we've tested here in Minnesota, they've been much, much tighter than the national average, 85% tighter, and all of them were at least 25% below the Army Corps standard. Maybe it's because we're worried more about cold drafts, frozen pipes that other people in other climates aren't concerned with. As tight as the buildings were, we did see reductions. We averaged a 9% reduction in general the reductions were somewhat more significant and more inexpensive for the leakier buildings. One concern is that the contractors tended to overestimate the amount of sealing work that would be done, and with these tight buildings, we're seeing very long paybacks for the air sealing work that was done. The mechanical systems we've shown are a significant part of the overall building leakage, and that's something that will need to be addressed, and there's a potential there for energy savings from tightening up those dampers. And the HVAC systems, while they are tending to pressurize the buildings, they're certainly not getting them to the pressures that HVAC designers would normally strive for.
Great. Thank you so much, Dave. I think you've done a great job of giving us an overview of the research and summarizing some of the findings. We will give people some time now. We don't have a lot of time left, but 5 or 6 minutes to enter any additional questions that they might have based on what we went over or didn't go over today. And I think that I believe we have a slide that we can put up our contact information, so that if you do want to contact either Dave about the content of today's webinar, that you can contact him via email, or if you have additional questions about how you can engage with the Center for Energy and Environment Innovation Exchange and sort of what we do here, you can contact myself via email as well. So one question that did come in, there we go. One question that did come in was, I think in reference to the economizers and air handler unit slides kind of earlier in the presentation, but how are these infiltrations and exfiltration levels determined for these different types of conditions or models?
Okay, so we used the pressure measurements that were recorded on the buildings, and were able to identify the periods of kind of occupied and unoccupied times and kind of bin them together in outside temperature bins, and we're able to see the trends in the building pressures. And from that, and knowing the building tightness, we backed out what level of flow imbalance was necessary to produce those pressures. And so we came up with profiles of building pressurization by outside temperature for both the occupied and unoccupied times. And then we added that to the contam model that included the building leakage areas. And then that contam model was run for the TMY data for the either Minneapolis area or wherever the building was located.
All right, thank you. We do have another question that just came in. For buildings that use active pressurization control, what recommendations do you have related to location of the indoor and outdoor pressure references and preferred methods of controlling pressure?
Yeah, I guess so we didn't talk much about the active pressure control. Some of these buildings did have active pressure control, and sometimes it's implemented properly, oftentimes not. I think that if you have a low-rise building, monitoring up at the roof is fine, and it kind of puts things out of the way. If you have a high-rise building, things get much more complicated. If you're trying to control pressures down at the ground floor, you'll certainly want to have your outside pressure reference down there. In some of the buildings that we've worked with, their reference was all the way at the top of the building, and they were making the mistake of assuming that when they dropped a tube down the center of the building from the outside, that gives them an outside reference at whatever floor they were measuring the inside pressure, which doesn't work that well and doesn't work that way. And in that case, we actually tried to do outdoor temperature compensation to adjust for the stack effect in that pressure measurement. the way that the pressure control that we've seen it done is either to control the return fan speed or the relief dampers. I guess probably I've seen it most in controlling the relief dampers. And in fact, when one of the buildings, a couple of the rooftop units had relief dampers and a relief fan that was activated based on the building pressure. The problem with that one is that it was just an on-off control. And so when the building pressure was near the set point, what we'd see is that the fan would come on for 2 minutes, and then the next time it was sampled, the building pressure had dropped, and so it would turn the fan off, and that would be off for 2 minutes, and then on for 2 minutes, and off for 2 minutes. So since it couldn't modulate that control, it was just cycling on and off. And I think maybe one of the biggest issues with the outdoor pressure control is that people tend to respond too rapidly to pressure changes. That when it's a windy day, you're going to see 15, 20 pascal pressure changes due to wind gusts. And if you're just doing a single pressure sample and trying to respond to that, it's easy to over-respond. And we've seen other buildings with air handlers where they drive their relief dampers kind of fully open and then fully closed on windy days because they don't put enough kind of dampering or lag into the control.
All right, great. Thank you very much, Dave. We actually do have a few more questions, but we don't have time to get to them right now. We will post those questions and answers as well as the ones that were answered on our webinar archive page, like I mentioned before, and we will get up the slides and this recorded webinar by the end of the week. Just one last thing is if you have additional interest in learning more about our research and our resources, our free newsletter will deliver this information to you on a monthly basis. You can sign up for this on your own. On our homepage, you can see right here on this slide in the upper right-hand corner where you can click and enter just a tiny bit of information and start receiving that immediately. And also, you can follow us on Twitter if you're interested, where the Innovation Exchange helps to share news and ideas on energy policy, technology, and research for relevant research and policy in the local and national levels. And we thank you again for tuning in, and we hope to see you at our next webinar on December 12th.